Hi, my name is Ryan, and I do consulting around Cape Town, in and around underground. That's where I stay, and I've been Rubying for a few years, since about 2006. And in the last few years, I've gotten more seriously into functional programming, particularly through Haskell. It's a major love fest for me in Haskell at the moment. But this isn't a Haskell talk. I just want to share some things that a pure functional programming language like Haskell really emphasizes very strongly. Some things that you're just absolutely unaware of in a language like Ruby or Java, even. Pardon the comparison. So I want to show you two slides of Haskell. This is the first slide. This is something you can do in Haskell. You can say something equals something else. And so it looks pretty damn familiar, but it actually means something quite different in Haskell. In Haskell, this means greetings is a string with a name, A. Okay, keep that in mind. You can also do this in Haskell. So A equals a string. A names a string. B is A, which is a name for a string, plus another string. This looks terribly familiar, and I'm sure. And that's the end of my Haskell talk, actually. So I hope that really pulls you in and piques your interest and gets you on the functional road. So really, that's it. What I just showed you is really just this. B being A plus Rubyfuza is actually, the compiler can look at that and it can say A is a value that we know of, and we can just replace it. And so B is a function applied to two strings, and the compiler can sort that out. So curiously, you can't do this in Haskell. That's where you leave the building of pure functional programming. So what's the difference, really? You've got this naming. A is named to the string value. And now you're trying to rename A to something else. And so that's something you do all the time, absolutely all the time in a language like Ruby. But you simply can't do it because in a pure functional language, those things on the left-hand side, those are names for things. So in a pure functional language, if I wanted to do that, I would do that compilation that I did before. I'd take A equals A plus Rubyfuza, and I would replace that A string. So the right-hand side is still totally functional. The left-hand side is a problem because you can't rename the same thing because it's a name. So this is a subtle point. You're going to hear it many more times in this talk. So just let it sink in a bit. This really brings out the difference between a value and a variable. Because the first piece of code I showed you, A and B are just values. On the other side, A is a variable. I'm changing it. It's got one value, and it points to, it's a reference to some place in memory that had that value now, and it had that value a moment later. So that's a pretty huge difference between pure functional and mutable. So variable is mutable, values are immutable, which means you can share them. So if you look at this, I'm putting some other stuff in between those two statements. So you got A is named to that string, B is named to another string, and there's some other stuff happening in between those two statements. If I only assign name values, if I only do value assignment in between this statement and this statement, there's nothing you can do there that's going to change what B is. B is greetings plus Rubyfuza. There's absolutely nothing if I only work with values that I can do to change that result, which is pretty incredible because the compiler can say what B is. So let's go to this side. What can the compiler say? It really depends. If I can assign things, that other stuff could include something like A equals 2. So I can't predict at compile time what the value of A is. It has no meaning when you have variables. So when you look at the compilation of pure functional programming languages and not, there are radically different environments to be in. You can say, the compiler can say so much more in the functional sense than it can in the imperative sense. So Ruby makes no distinction between this kind of setup where you have values, which are just really renaming things, and where you're actually reassigning stuff. As far as Ruby is concerned, linguistically anyway, there's no difference between those two. From a Haskell point of view, there is no variable. There just ain't. And that's quite a crazy, crazy idea. And it's very, it can be very limiting to start working in functional programming. In fact, if you've never worked in a pure functional programming language, you'll find that you're in a straitjacket quite quickly. You can't move, you can't assign, you can't do anything that you're so used to. You can't get out of the blocks. It feels like your keyboard doesn't have an enter key. You just can't do anything. Eventually you can, by the way, so don't take that too seriously. Scala makes a big distinction between value and variable. Scala says value is not variable, and it treats it differently. So in Scala, if I wanted to do that, I say value. A is a value, B is a value. And so now the compiler can make use of that information, and it can resolve all values at compile time. And it can make optimizations and all kinds of things. On the right-hand side, I'm saying A is a var, and so now I can reassign it just like in Ruby. So what you can see is that value and variable are fundamentally different things, something that is treated in exactly the same way in Ruby. They're so different that some languages deny their existence, variables, and other languages make this point of this distinction. So why is that such a huge issue? Why does it matter? So obviously I've shown you now from a compiler point of view, it's a very different situation. You can prove much more about programs, functional value-based programs. But what difference does it make to you as a developer? And so I want to go into that a little bit and just share some thoughts. So look at that function. Add A, B. There's no assignment. It's just A is a value, which is coming in there. B is a value, which is coming in there. It's adding them up, and it's just returning the value. So there's absolutely no mutation going on. So this is a pure function. This is Ruby. So practically, it's not actually pure because it's all objects under the hood. But linguistically, this is a totally pure function. There's no side effects. How about this function? So I'm still taking in A and B, but I'm assigning something calculated based on those values to something else, and then I'm using that in a subsequent calculation. So I could say that this is a pure function still. So even though that is an assignment, I could say that that is just a renaming, because I could treat that as a renaming. I'm not actually assigning. Why? Because I'm not reassigning the value of Z. I'm assigning it and I'm using it. So Z is a value, not a variable. I'm not changing it anyway. So this function is pure. And in fact, you can write that. There's a syntax in Haskell to write exactly that kind of thing. So what does it mean? What does purity really mean? Have a look at this function. So I'm taking now, instead of A and B, A is sitting on some scope next to the function. B is still being passed in. And so I'm mutating now A, adding in. So I'm still doing A plus B. But now A is kind of stored somewhere outside of increment by. It's as if the pure function has been smeared and some of its instance variables have spilled out. And so this is not a pure function. You could consider this a closure, meaning that it's a function that grabs anything that it references outside of its scope, and it just binds it. It doesn't care where it is. It will just bind it. So that A is bound to that one. It's coupled to that one, and I'm changing it here. Have a look at this one. So now I've got some constant. It's a value. Constant is a value, and I'm using it there. So even though I'm not changing extra, it's a constant, I'm still using it. So there's this issue of, there's two issues going on here. If you look at A, there's a coupling from here to here. These things are coupled, and the coupling is across the method boundary. Again, with extra, there's a coupling, but there's no change in values. So they're not equally evil, these two are side effects. This one is a side effect. This is not. This is just a value. But it's a coupling that breaches your abstraction. So I want to make this distinction between coupling and side effects, that in order to have a side effect, I need to have some kind of coupling. But there is coupling that doesn't lead to any side effect. It just leads to constraining your design, but it's not a side effect. And so it's like coupling is like a pipe along which side effects can flow. So I want to show you every time, the way that we lay down pipes all the time, we connect things all the time, and through those pipes we can let side effects flow. So I want to just bring that, make that more explicit. So there's that increment by function. It's still referencing that balance variable outside, being initialized with that, defaulted to 0. So it's exactly that function still. So inside the class, I've got this smeared out function. Increment by is not pure. It's smeared out. And yet on the class calculator, I have a reader for balance. So if I'm standing outside the calculator class, balance is read-only. So it's a value. But inside, I'm going nuts with it, and I'm changing it, and I'm assigning it all the time. So it's interesting to look at it like that, because a class is like a boundary for side effects. What you're really saying is, from an object-oriented sense, you're saying, inside this class boundary, I'm prepared to make a lot of side effects. In this class of mine, I'm actually keeping it pure on the outside. It's just balance is just a value. But I'll show you one that's meaner than that later. So if I wanted to test this increment by function, how would I test it? The smallest testable unit for that method is the class, because the method isn't pure. If it was pure, I could have tested it directly. But now to test it, I have to use the increment. I have to create a new calculator class, instantiate that, call it on that. So you might argue and say that that's all right. I mean, this is a pretty expressive test. It's telling the story reasonably well. But what about if that increment by becomes a really, really hectically complicated calculation? So there's still some readers. I've put some more in. Now I've got some accessors, meaning these are variables. These were values. These are variables that I'm projecting outward from my object. So I'm opening myself up to side effects coming in from remote objects. I've got an initializer with a whole bunch of things in here potentially. One of them is an object, another object, on which I can call a destructive method. So I've got the calculator object being initialized by something and doing something destructive in the initializer on another object. So I hope you guys don't do, I'm sure you guys don't do this kind of thing very often, but it creates an incredibly deep coupling. And basically you're connecting two objects with a big fat pipe, and the side effects can just flow happily through that. So if I wanted to test wicked calc now, this becomes a lot harder because I need to, let's say I know that you wrote wicked calc a week ago and I need it. So I'm sure you've been in situations where you ask someone for a piece of code, they say, sure, they've written it. And when you start to use it, you find that the setup is unacceptable, typically. Maybe you have to instantiate a new class and run some pre-initializing functions, and then you'll call wicked calc. So if I wanted to share wicked calc with you, this is not a good way to share it, because I'm forcing you to test it and to understand it in this broader context. So back to our earlier class with just this little incrementer. The first thing I can do to make, to kind of separate side effects from values in this class is this. So I've extracted an add method, and I'm using that adder in the increment by. So I'm not doing it directly here. So this looks a bit pointless, but imagine again that add is fundamentally more complex calculation, maybe a series of calculations. The huge thing that's going on in this slide right here now is I've separated out something pure from all of this. So it doesn't look like much because it's a one-liner that's now pure. And all this other stuff is still side-effecting code. But for every method, for every increment by, there's potentially something you can extract. And you do this over and over again. You'll find that this pads into a whole little layer. It's like you have the side effect class, and then you have a pure functional layer just below it, just to the side, however you want to arrange it. Really, that's a design choice. The thing I'm harping on about here is separating those two things. In an example like this, not very interesting, but blow this up into a seriously complicated situation. Or actually just a real-world situation is enough. So you can, by doing this, if you look carefully, what I've done is this is composition. So I've composed increment by from this add, this pure add function. So I'm taking something that was impure, I'm taking something pure out of it, and now I've got a separation. And now when I collect these things, I can put them in a different class. They become, add is much more testable than increment by. Increment by can only be tested in the context of the class because of its gut spilling out into the class. Add has absolutely no affinity to this class. By that I mean it doesn't access any local instance variables, nothing of the sort. And so you can think of methods on objects like little plants shooting roots into an object. And some methods shoot much deeper roots than others. This one has no roots. This one has that one, balance. So when you see things with no affinity for a class, they really shouldn't be there. So basically you can start really mopping up all the purity. You can milk this class for purity. You can really milk out the functions out of this. So you could say that it's hard to make a real meaningful example actually in this case because it becomes interesting at greater complexity. But you add that up over time, you add that up one line at a time, and it starts making a difference. Another thing that many of you are doing all the time is you're doing this kind of thing instead of this kind of thing. So instead of having an array, which I'm iterating through, and I'm doing something to it, and then I end up with an array at the end that I can start using. You can do this instead. And so by doing that, you're doing this all the time. But by doing that, from a side effect perspective, you've actually taken a variable out. And it's just gone. You've taken a variable and did the same thing with a value. And so that's why those iterators are so amazing. That's what we intuitively, even if we're not conscious about it, love about them, is that they don't have these dangling little variables. And in fact, you could have variables inside there even. But I think the thing is that side effects is about minimizing, taking away any undue side effects. It's not about reducing side effects. You cannot avoid side effects. You cannot write anything useful that doesn't interact with the real world and so on. But you can sure as hell minimize them, you can limit them and so on. So that's what I'm talking about. I'm talking about some kind of middle road of managing this complexity. It's not about doing away with them. So in this example, it's a good example of undue. This is undue side effect because I can do the same thing without it. And so this one costs a lot more because this is a variable. If in between upcased and r each, I can insert any number of lines of code that will totally foobar your tests. And yet, if I keep it with values and pure functions, I can't because it's just values upon values. You're doing this kind of thing all the time also, perhaps. It's the same example as before, but now the little calculation, the little operation on every item becomes more complex. In this case, I'm doing something trivial like 2 things, adding this thing to that thing. But imagine this becomes a multi-step serious calculation. This is a more functional form for that. I can, essentially, I go through the whole list, I do one transformation. I go through the whole list, I do another transformation. So obviously that's less, you could argue that that's less efficient than that, for sure. But that's more maintainable than that. So that one has that trade-off. And if it doesn't matter, you're probably better off by composing into multiple functions. So in terms of taming side effects, the things that we've looked at so far is limiting them. So this issue of milking your classes for pure functions, this is what I mean by this, is extract the maximum purity through composition from your class code. Separate out the pure from the side effect ridden. And then you can use functional forms. So that sounds like you can't do that much about them, really. But if you look at what other paradigms do with it, in Haskell, you do have side effect capable code, and that's where monads come in. Alternatively, there's a concept of software transactional memory, which is an alternative way of limiting and constraining side effects. So it's quite, it can be easily thought about pure functional languages that there are no side effects, but they're there. They're just constrained. They've made them very explicit. And there's also a sense of conventions around using them. In Erlang, you have a similar thing where your side effects are limited to messaging between immutable objects or values. So they're there. The side effects are everywhere. And the issue is, what do you do with them? How do you structure them? How do you tame them? ActiveRecord is an example of taming side effects through conventions. Because if you think of an ActiveRecord, think of a few ActiveRecord models connected in a graph or a tree, and they're up here, and underneath, in the netherworld, there are data tables, and there's data, and maybe file systems, or whatever, being changed in a mirrored way to your ActiveRecord objects. That's, after all, the point of the abstraction. And you can think of ActiveRecord as a way of really using a lot of convention tame side effects and to say that if I'm going to have a foreign key table, foreign pointer from this table to that, I will name them the same. That's a way of saying, I acknowledge that there's this coupling, I acknowledge that there's side effects, but through conventions, we can make them more explicit. And I would say that if you, in your coding house rules, in your teams, whatever they are, you probably have a good deal of rules around taming side effects already. So you might be saying things like, never change something like this, or only change it like that, or never name something that you're going to change like this. And so those things are your attempts to tame side effects. And so ultimately, moral of my story is side effects actually cost an enormous amount of time and energy. They are the things that typically couple your system. When we talk about brittle software, why does it become brittle? Because of coupling and effects that are far away from causes. So I think that's another big thing for me in all of this is how far is your effect from your cause. So in a pure function, add AB, there's no distance, there's only value. There's absolutely no distance between cause and effect. In some of the other examples, it can be huge. And in some of the software that you're running and GitHub, you know, the effect and the cause can be as on opposite sides of the planet. But in terms of your code base, then, you can manage how far the causes are from the effects. So, you know, Stuart's talk earlier about service-oriented architecture is interesting because that's a macro-level story going along the similar lines of looking at side effects. Because one starts looking at how do you test services? What is their testable, smallest testable unit? And how do they affect each other? And how are you prepared to let them affect each other? So service-oriented architecture actually touches a lot of these things on a macro architectural scale. But you can need to take all of those ideas around to the micro, nano level of every line of code you write. I think every inch you gain in a code base that grows over time is worth the effort. I think why we bind ourselves in side effects like this is because they accrue at a pace that is much more, it's too slow for us to perceive, really. And I think we need to kind of own up to the fact that we don't feel the cost. Every time we make a little assignment, every time we make a coupling, we don't feel the cost. We're like frogs in a boiling pot. It takes us a while to figure out that we're cooking, and then it's too late. The difference between how sensitive, how small the change feels at the time and the effect later on is absolutely massive. So what I mean to say is that you can't actually trust your intuition on the micro level, because you take these micro level steps, you roll, multiply it out by a gazillion in a code base grown by many people, and all those tiny little couplings make the difference between rewrite and refactor. So that's the end of my story. Thanks. Questions, comments?
One thing that I can say is that relevance is anecdotal somewhat. It's like whenever I see a lot of heavy trouble in code, usually the number of user tests is pretty small. It's very many at all.
Yeah, I think it's inversely proportional.
Yeah.
Yeah. Great. I hope you go and, learn Haskell. You want a number? Too much. Too much. Yeah. I think it's impossible to quantify, but I just want to say, in a bounce back on that front, I think it's an interesting thought experiment to make like they cost money. So if you, let's say you're sitting down, you're about to write some code. Just once, do this. Count your assignments, minimize them. Count your side effects, minimize them. Once. For one, let's say 1, 2, 3 hour session. Just do it once. Because they're basically like, side effects are like these, they're not bad things. They're like these precious little gems that you should very sparingly use. And we've got an infinite budget in Ruby. We could just go nuts. And we just blow them all. And we get into trouble. So in Ruby land, it comes down to discipline and awareness. The compiler isn't going to help you. It's not there. Cool. Thanks.